Hello guys, this is Brett from Steam Tutors, and in this video we're going to take a look at binomial heaps. So what is a binomial heap? Well, as you can see from my drawing, binomial heaps are collections of heap-ordered binomial trees. I have listed the operations they perform and their associated amortized costs in the top right for you. The properties of binomial heaps are, binomial heaps use a min pointer, which points to the minimum value item in the heap, and there is at most one tree of each rank in the heap. There are two different types of binomial heaps, and those are lazy meld and eager meld binomial trees. The key differences are that lazy meld will allow several binomial trees of the same rank and will wait till the next delete operation to restore the second property I've mentioned. Eager meld binomial trees will check for the need to perform a meld after every operation. As a result, there is a very significant property of eager meld binomial heaps, and that is that the binary encoding of the binomial tree ranks can tell you how many nodes in the heap and be used to infer in reverse the structure of the heap based on the number of nodes in it. Let's use this heap as an example. So we have a binomial tree of rank 0. We do not have one of rank 1. We do have rank 2. And we do have rank 3. And what we get is the binary representation of the value 13, which is in fact how many nodes we have in our binomial heap. Keep in mind, this is not always the case with non-eager binomial heaps. For those, you must have some information about at least some sequences of operations performed. Okay, next let's look at some examples of how operations are carried out on a binomial heap. The first operation we are going to go over is insert. In this example, we are going to insert the value 2 into this heap labeled original. I would like to point out that I am representing where the minimum pointer is pointing by highlighting it yellow. So the first part of the algorithm is to insert the value into the root list. At this point, if you were implementing a lazy union binomial tree, you would check to see if the min pointer needs to be updated, and you would be done. This is how lazy meld accomplishes a constant time execution for insert. But for eager meld, we must union binomial trees of the same rank until we no longer have more than one binomial tree of each rank. So in this case, we are fairly lucky, and once we union the two violating rank 0 binomial trees, we don't run into any other conflicts. However, this can cause a series of melds to occur, which we'll see later. Also notice, to meld it is as simple as removing the larger root key from the root list and pointing at it with the root of smaller key values. The last operation to perform is update min pointer, and that completes the insert. Next, we are going to decrement the value of 20 to 4. This is just a simple heaping up process followed by checking to see if the min pointer needs to be updated. So if you need to, you can pause here and study the operation, but I'm going to just move on. Next, we're going to delete the value 4. The first step to delete is to remove the node and promote all of its children to the root list. Next, we will need to check for any rank conflicts and meld binomial trees until no conflicts exist. This is done by starting at the smallest rank and moving up. First, we will find duplicate rank 1s, so we meld them to create a rank 2. Now we find duplicate rank 2s and meld them to create a rank 3. At this point, we no longer have any conflicts, and we are finished. Well, this has just been a brief introduction to binomial heaps, but I do have a closing remark here, and that's that the main takeaway for most advanced data structures and the reason we describe them in terms of their amortized cost is that if you're going to spend time maintaining structure, it is better to do so in bulk instead of at every operation. There is a balance to be struck with performance through varying degrees of structure. We saw this with lazy union binomial heap here, where it took advantage of the fact delete was already going to perform the restructuring, so we could just wait on the union operation and get better performance by waiting for it to be handled there. This has been Brett from Steam Tutors, and if this video was helpful, please subscribe.